Greetings, everybody. I have about a minute before the top of the hour. I just wanted to step in and let everybody do kind of a little bit of an audio check beyond the announcement they kept hearing. We will start at the top of the hour, which is just in a few seconds here. Well, hopefully you've joined us today for the ASBI March webinar to hear about the HART Airport Guideway and Stations project. We have 3 presenters for you today. So I will move quickly through the introductions so that we can get on to our feature presentation. I am Greg Freeby, the Executive Director of the American Segmental Bridge Institute. This is my contact information on screen, my email address if you need to get a hold of me. I'd also encourage you to follow me and the American Segmental Bridge Institute on LinkedIn. It's one place you'll find about not only our monthly webinars, but also other activities and events we have going from time to time, and also just some posts that we do almost on a weekly basis about segmental bridge technology. Some quick announcements. Our April webinar, I encourage you to go ahead and sign up for that. It's already up on the website if you want to register for that. April 27th from noon to 1 Central Time. We're going to be talking about the extra dosed fin back bridge design that was done for the Selman West extension. Also want to mention next Monday, or a little over a week, is April 11th. Our grouting certification training is going to be held in person at the J.J. Pickle Research Campus here in Austin, Texas. This is the only training session we're offering this year, so if you or people you know need ASBI's grouting certification, I'd encourage you to sign up for this training. If it's not required for your projects, I would still encourage you to sign up. It's a great opportunity to really get some more in-depth understanding in how post-tension segmental grouting works. Another event that's coming up, I'd like for you to get on your calendars, October 31st through November 2nd at the Hyatt Regency here in Austin, Texas. We'll be hosting our annual convention and committee meetings. So then the other thing I'd like to make you aware of is we do have a new publication coming out, which is actually relevant to today's topic. ASBI formed a work group for the design and construction of segmental bridges that support rail, and that is light rail, heavy rail, any kind of rail structure. This publication has actually been completed. The first edition we're about to roll out. It should be available on our website early next week, if not by the end of this week. So we have a March publication date. The publication is really not all about how to design a bridge for rail. Instead, it's what are the things one needs to know that are different when you're designing a segmental bridge that is supporting rail. So some quick instructions on how the webinar works from your perspective as the user. If you lose connection at any time during today's broadcast, you can rejoin. Just click the link that you were provided. You will miss content while you're away. It's sort of like if you step out of the room during a live presentation. We will be doing certificates of attendance. We do ask for a minimum time that's required in the session. Since it's a 1 hour professional development hour, we need to be as close to that hour as possible. Having said that, I understand we may run a little long today with Q&A that may run past the top of the hour. If you need to sign out before we're done with the question and answer, that's perfectly acceptable. We understand folks have other commitments. As far as the certificates for completion, please allow a week for us to get those to you. We don't use an automated system that just generates and sends out certificates to everybody that logged in. We actually have to verify your time and attendance in order to meet our requirements for RCEP in terms of issuing certificates. So we're going to do question and answer at the end of the presentation. and I'll go over quickly how that's going to work. You should find on your control panel a little pull down tab that says questions. You can click on that and then type in your question. We don't have the ability, with so many people online, we don't have the ability to take questions live in terms of audio, but we can take them live in writing. And go ahead and put in those questions as you think of them during the session. You don't have to wait till the end. And then we will have a moderator do a live Q&A with our speakers at the end, and he will use your questions that you submitted to run the Q&A. If you're on a mobile device, you should have a little question mark in the upper right-hand corner. You can click on that little question mark and again be able to type in your question. So with that, we will move to our presentation. And so first I will introduce our speakers, and then we will and then I will turn control over. I'll go ahead and introduce our speakers in order. Our first speaker will be Mr. Ben Morris with Parsons. Ben has over 13 years of experience in design, construction, inspection, and management of complex concrete bridge projects across North America, working extensively in the design build environment. He has a depth of experience in rail structures in addition to roadway and pedestrian structures. On the HART AGS project that you'll hear about today, Ben was a lead superstructure engineer before taking on the responsibility of on-site design services during construction, and he's been doing that over the past 4 years. Prior to his work on the HART AGS, Ben was the structures design manager for the California High-Speed Rail CP1 package and is currently delivering the Edmonton Valley Line West Rail Line project. So our second speaker is Tony Gargaro with McNary Bergeron. Tony, with over 13 years of experience in transportation project delivery, Tony believes that construction engineering can provide practical, cost-effective solutions to meet the challenges of today's complex bridges. Leveraging his experience in field supervision and construction engineering, Tony leads teams of engineers to deliver projects through the design build and design bid build for a variety of contractors, transit authorities, and state DOTs. Then our third and final speaker of the session will be Mr. Jeff Miron. He has over 15 years of experience in the heavy civil construction industry, constructing complex bridge, transportation, and marine projects throughout his career. He's currently serving as a structures manager on the HART AGS project, the third phase of a 20-mile concrete segmental guideway connecting downtown Honolulu with the western suburbs by means of a 21 station network. And you're going to see today a lot more detail on this project. So with that, I will turn over to our first presenter, Mr. Ben Morris. You'll see a brief pause on your screen as Jeff takes over and becomes our presenter. Great, Jeff. Ben, we see your screen, and I think we're ready to go. If you're unmuted.
I think I'm ready. And Jeff's my brother's name, so I won't take any offense to that.
Oh, did I say Jeff?
Well, welcome everybody. Thank you so much for taking out time of your busy days to learn a little bit more about our project and segmental bridge industry as a whole. As Greg said, I'm Ben Morris with Parsons. Today we're going to talk about a project that I've had the privilege of working on for about the past 5 years, the Honolulu HART Airport Guideway and Stations project. Oh, I have to click here, and now we go. Okay, so today we're going to talk a little bit over the overall project, what was the HART AGS segment, and then the three main areas that I want to talk about are the entry into the airport with a 3-span continuous unit. A couple spans down from that was a limited access tight curves near the lay stands, if anybody's ever been to the Honolulu airport. And then what we like calling threading the needle, which was a limited overhead and a limited limited clearance below the structure. And then Tony will pick it up to talk about some of the interesting construction engineering. And Jeff will finish up with just taking the contractor's perspective of building on the island. The Honolulu AGS project, the owner is the Honolulu Authority for Rapid Transportation, or HART. They've been a wonderful client to work for. I have only positive things to say about this project and them as an owner. The airport guideway is one phase. It's phase 3 of the overall project, starting just a little bit of the Pearl Harbor station and then continuing all the way through Middle Street Station through the airport. And it was awarded in 2016 for $875 million. It's 5.2 miles of elevated precast segmental guideway, 4 elevated stations, which were supported in part by the guideway as well. Dual track, 188 spans, typical 140-foot spans with an 8'6" depth. This is a look at the, on the left, the typical guideway spans, and on the right gives you an overview of the project corridor. Up here on the upper right is Pearl Harbor, going around H1, turning past the tarmac for HIA, and then trying to get into a tangent alignment in time for the HIA station, putting some pretty tight curves into this area. Focus of today's presentation is in the HIA area, going over the tarmac here and getting past the parking garages. You see all the operations roads, elevated ramps, and then this is where the future station will be located. Well, it is currently located. So we have 3 main areas that I mentioned earlier. Airport entry spans 522 to 524. This was a 3-span continuous unit. And then spans 535 to 540, another very tight radius curve with real limited access and footprint that we could put piers down. And then my personal favorite was a limited vertical clearance and shallow box area in what we would call Reach D near the Lagoon Drive station. Overall, with this 3-span continuous unit, our goals were to use the project-wise span-by-span erection method and use the project articulated gantry. So try and minimize impacts on the way that we were doing this, and also minimize impacts to the operations of the airport. You know, this is a very active international airport, and with a post office nearby that also needs to be operational nearly 24 hours a day. And then incorporate, even though we were doing an atypical span arrangement, incorporate as many of the project details as we could to minimize modifications to the forms and construction techniques. The pier locations and alignment were set by the owner and couldn't be changed. And in this case, we had a 140-foot span with a 400-foot curve on it. Once again, this is dual track, single box, so pretty tight radius for an eccentric load. So we ended up throwing in a 3-span continuous unit for the stability of the spans. This area is also the highest portion of the project, so that we could get up over the airport tarmac right here. And the way that we did that is we took just simple span construction techniques, erecting the first span when span by span methods, and then made continuity by overlapping the post-tensioning tendons at these pier segments. And then launching the gantry, and Tony and Jeff will talk about the unique challenges of the construction engineering and gantry in this 140-foot span and this tight curve, and what was needed to be done to get this around the corner. And then the end span erection, and each time we launch and erect the span, these tendons get overlapped, and we stress from the leading end, one end stressing only. The key to using the span by span for the continuous spans was to create a continuous pier segment, which we basically just took the typical expansion joint pier segment and truncated it. So this is what our typical EJ segment looks like. You can see the sloped diaphragm right here. This is the span side. This is the EJ side of that. And that's what it looked like in the yard. This is the span side of the EJ segment. And as you can see, we basically just shortened it up, truncated it through the diaphragm, and this allowed us to use a lot of the same elements from the precast yard, and really the only things that needed to be changed were some of the core forms and the bulkhead forms, and a pretty slick detail. Put those back to back and match cast them, and all of a sudden you have a nice full pier segment that has anchorages on either side that can be stressed together for these pier segments. This kind of shows how these anchorages overlap, and you can see it's quite a busy segment with the anchorages on one side with the exits, 4 tendons plus a future tendon, and then we needed to add some PT bars in the top to help with both ultimate moment and stresses in this now continuous high negative moment region. And so this is kind of the overall PT layout, seeing those pier segments in use. We utilized a lot of the same typical segments within the span and tried to only utilize a unique segment in these pier segments. This is what that 140-foot span looked like in the center. We had to add some top PT, so we ended some isolated top anchor blocks for the negative moments over the continuous piers, but otherwise utilized much of the same details as a typical span. And the end span, same as the first, and we did introduce some closure pores in here to help with the construction phasing and match casting. And then just a few spans up station, we had another tight curve area that I spoke to a little bit earlier. We wanted to optimize the pier locations and design within the HIA, the airport requirements, and avoid costly utility relocations and impacts. Use the standard project details with minimum modifications, and then finally, we had a couple gantries on the project, but we want to avoid any specialized equipment or reconfigurations that were needed. And Tony and Jeff will dive into how we were able to accomplish that. The RFP span layout was pretty, short spans, tight radius, quite a few piers. We ended up reconfiguring some of these locations, keeping some short spans for stability, and you can see all these access roads down below. We had really limited locations to put down towers, as well as these lay stands right here in this parking lot and this over here. The 118-foot span ended up with the only pier in the lot itself, and that was a big success to get 2 piers out. And as you can see, our numbers jumped from 537 to 539. We're able to optimize that down and eliminate a pier from the RFP plans. This is kind of the work area, nice congested area confined by ramps and roads, and they ended up getting in there, putting in the piers, real tight access for major construction while maintaining all kinds of daily operations for flights coming in and coming out. And you can see the one pier in the parking lot itself here, and we were able to avoid this utility, which is a major location that would have been necessary in the parking lot down there. Tony and Jeff will talk a good bit about the gantry operations in this area, but one thing to kind of, the benefit of putting that 68-foot short span in here is, as we were coming around this corner, we needed to make sure that the nose of the launching beam and the gantry itself wouldn't clip this airport parking garage, and they have some great pictures that show just how close in we got, within a couple feet to get around that curve. Post-tensioning of the tight radius curves utilized a lot of the same details as the typical span by span, with the addition of this top tendon. And this top tendon, even though it's simple span, it's not used for top stresses in the classic sense. It's used for torsional shear stresses. And that's why it was needed to be added in. But that was really the only special detail that got added in. But with the simple spans and the tight curves, we did end up having to utilize uplift capable disc bearings. They were provided by R.J. Watson, and that was one of the unique features of this bridge. These do see uplift in the service condition. And then the last area that I want to touch on is the airport guideway or glideway area of the job. There was a FAA requirement for minimum vertical clearance in the glide slope above the runway, and so they had to be able to get planes above this OCS and sorry, not OCS, over these spans with the train clearance, but also it was over an active roadway, trucks, a lot of industrial businesses. So we ended up with a resulting maximum structure depth of about 4'6", and we had, once again, limited pier locations because of all of those businesses and utilities in the way, and we still wanted to use a lot of the typical details from the rest of the project and avoid making costly modifications. So this gives us a sense of the project area that we are on along Uolena Street, which then goes over Lagoon Drive. You can see the guide path here, and what that ended up doing is setting our alignment down in a real low alignment to get the glide path window achieved, while also maintaining the clearances to the roadway above, and then also getting up in time to allow for a full depth box in this 150-foot span over Lagoon Drive. And what that basically resulted in is literally an inch above and an inch below this precast box. We were within those constraints. So that set our maximum segment depth. And in order to achieve this 4'6" box, we used a lot of the same shape, truncated the webs and widened the bottom slab. We did end up having to increase the width of the webs to get them up to 12 inches for shear stresses, principal shear stresses, and ultimate shear capacity. And as a result of the wider bottom and the thicker webs, these segments, even though they're half as deep, were basically just as heavy as the full depth segments themselves. And this gives a sense of just the scale of even fabricating these, how tight it is in there. A lot of the similar details. We did end up having to incorporate, a lot of new details for the blocks in this area, where we would be deviating multiple tendons all at the same time. The anchorages, we had 4 tendons plus a future tendon. So the anchorages of the continuous pier segments were very, very, very busy. And then just to make matters worse, we actually had straddle vents, integral straddle vents at 591 and an interesting shaped straddle vent at 592 to keep the clearances that we needed above the roadway. You can see all the anchorages piled into this pier segment. And in this particular location, in order to set the wedges, STG needed to block out this cheek wall here, which will ultimately be hidden behind a shear block. So you can't see this from street level, but to get access in there, they opted to block out cheek wall. And just to give you an idea of how congested these very shallow straddle vents are, this is the PT layout for straddle 591. A lot going on in these segments. And then this is just a larger detail of 592. We ended up having to put a construction joint in the stem, the back wall of the straddle vent to gain access to stress the front end. This is constructed left going right. And then they cast this straddle, once this is stressed, they cast all the anchorages for the upstation span into this back wall. And then all they need access here is just the dead end anchorages to set the wedges. And some pictures of those 4'6" pier segments being placed. And, you know, this is truly a doghouse. You know, we talk about these access openings being shaped like a doghouse. This is actually the size of a doghouse. And with that, I'll have Tony talk a little bit more about the particulars of construction engineering on this project.
All right, bear with us for just a minute as we change presenters. Tony, you're up. We can see your slides.
Great. Thanks, Ben.
And we can hear you as well.
Even better. So this project was really interesting for the construction engineering because we're able to be involved with pretty much every part of the project from start to finish. Beginning in with the constructability review, we helped the contractor and designer develop details that were buildable and met their preferences. Moving into the equipment selection, we ended up with the 1 conventional and 2 articulating gantries made by Deal that you see on the right, but several other types of manufacturers were considered. And once we knew the gantry types, we were able to provide preliminary loading to help progress the early design. Continuing into geometry control, there were over 2,700 segments over the 188 spans. And we also helped STG with the day-to-day construction support. And then what we're going to take a deeper dive into today is the erection manuals and false work. So the launching gantries require a unique sequence for each span that we call an erection manual. That's because the procedures are different depending on the span length of the one being erected, the tenon layout for that span, and the length of the span that the gantries launch into. Each span has a stressing sequence, which we'll talk about next, and a launch procedure that we'll discuss in a video. So to start off the span erection, we need a stressing sequence. That sequence starts after the segments are hung from the gantry and stressed together with temporary PT bars and epoxy. Some spans require an individual analysis, but for the most part, we're looking at groups of spans. So for example, say 130 to 140 foot spans without top slab tenons. We combine the span post-tensioning layout, which is given in the drawings, the stiffness of the concrete box section, which we can calculate, and the stiffness of the gantry, which we find by modeling the main girder in RISA as shown on the bottom. Some things to keep in mind, as I'll show in the next few slides, are the top and bottom fiber, making sure they stay below the tension and compression limits, and the capacity of the gantry hanger system. So this is a typical 140 foot span. The gantry you see here is the conventional type, but articulating is the same idea. We have our gantry hanger bars, our span PT layout, our tension and compression limits. So first step is we stress our first tenon. Now as the span starts to hog up, we can see how load is being shed from the interior hanger bars out towards the exterior hanger bars and the bearings, and we start to approach our tension limit in our top fiber. So the next step would be to lower the gantry an inch. We can see that the exterior bars have been completely unloaded, and then we start to load up the center bars again. We've also relieved our top fiber stresses here. Next, we stress the remaining tendons. The center bars load is shed again from the center out to the exterior, and we're okay in our tension and compression limits. Sometimes the spans require us to do another set of stress attendant and then lower, but in this case, it wasn't necessary. And then we released the span from the gantry completely, and we're at the final design condition after span erection is complete. So after we erect and stress the span, we need to launch to the next one. Overhead gantries are usually custom designed and built for the project, which means that to economize the design, they're pretty near capacity for the typical spans, say plus or minus 10 feet. Outside of that range, we need to start considering special procedures, such as removing elements of the gantry or adding elements such as false work or counterweight. For each launch, we need to monitor the capacity of each component, the stability of the gantry, as well as the global stability of the span. On the next slide, I'll show you a time lapse of the launch and talk through what's happening at each step. So here's an overview of each of the components before we start. You have your main girder here in blue, your support beam here in orange. The main supports for span erection are the rear support on deck. That's the one that can drop wheels and be dragged across the span. The fixed leg sits on the forward pier. Supports for launching are the rear mobile support and the front mobile support. And the supports on the piers sit on what Deal calls a pier traverse. That's erected by a crane in advance. And the thing that's doing the most work here is the fifth wheel. That's the one, as you'll see in the video, that can launch the main girder, launch the support beam, and manipulate the support beam. This is a typical gantry launch. This is actually the first launch on the project, and so there's a couple of operations that are done, especially with the support beam to test the gantry, but it will show you how it can move along the slope of the bridge and side to side around a turn. So we picked this up just after the wheels are set down on the rear mobile support and the main girder has launched a little bit along the support beam. So the main girder will continue to launch until the fifth wheel is over the forward pier, or what is here the rear mobile support. After that, the winch will grab onto the back of the support beam and assist the fifth wheel for launch. And the support beam launch will continue until just shy of the balance point, at which point the fifth wheel will be locked and the winch will be released. Now, as part of the testing operations, you'll be able to see how the support beam can be moved up and down to account for changes in grade on the bridge. Like that. And then side to side around a curve. Now we'll resume kind of the more typical sequence, running the front mobile support over the forward pier, attaching it to the pier traverse that was erected by a crane previously, and launching the support beam. And just before the end of that launch, we'll see how the fixed leg can move side to side as well to get around those tight curves. Now the fixed leg will be moved into its final position over the forward pier, attached to the pier traverse, and it'll change places with the rear mobile support, which will be moved out, trade places with the front mobile support. Now it's not going to show it on this video, but the last step of the launch is to simply move the front mobile support ahead a few meters, and now we're ready to erect span number 2. So one of the trickier parts of the project that Ben mentioned earlier was the airport parking garage. This is the parking garage for the Honolulu International Airport, and it drove several design decisions for Deal, who was a gantry supplier, and it influenced pier locations for the structure since, as you can see, the support beam had to move forward and rotate several times to get around that parking garage. The tightest clearance was a bit under 6 feet, and as you can see on the pictures on the right, it was a pretty tight fit. That's a good example of a well-executed plan. Moving on to false work, there were several locations that needed false work on the job, but I wanted to highlight these 3. First was the outrigger tower coming into the tight 400-foot curves in the airport. Next was the short box continuous spans that Ben talked about earlier over Elena Street. And last was the hybrid construction near the end of the alignment at Pier 622. So outrigger tower, due to span lengths along the 400-foot curve, the support beam needed what Deal called the special traverse, which was supported by the pier and an outrigger on the side. We threw just about everything I could think of to throw at an EFCO tower. Because on one side we had a utility vault that we needed to span over. On the other was a retaining wall we needed to stabilize. There was an offset straddle bent, and finally an actively monitored jack to control the deflections. In addition to the false work design, we needed to check the permanent pier column since we were loading it in a way that was not considered in structure design. So we enveloped the minimum and maximum deflections in the false work to get the axial force and moment in the column, and checked the interaction to make sure that the loading was within the allowable limit. Next is the continuous span false work. This is the end of the continuous span that Ben was mentioning, and the upstation end needed to be accessible for stressing. This meant the back wall needed to be poured after the span was erected, and the whole thing needed to be supported during erection of the next span. So the original plan was to place the front support of the gantry on towers in front of the straddle bent, but due to utilities and other buried structures, that was ruled out. Instead, what we ended up using were EFCO towers with simple headers, and then to determine the stressing sequence, we ran an analysis similar to one that you saw earlier to check the span and the straddle bents. And then after the spans were complete, the gantry was simply walked across the finished structure. Last for today is the hybrid construction at Pier 622. There wasn't much of an option here for pier locations. The road you see is the main access in and out of HIA. And as you can see, you can place a pier to the left, one in the gore area in the center, and another in the median on the right. The maximum span for the gantry was 150 feet. And so at 166 and change, we needed to add false work. So the solution here was a hybrid construction model, and we designed some false work to support a temporary pier head on the center pier. So the gantry launched to the pier head so that the fixed leg was over the downstation pile, erected the back span, launched, and erected the forward span. It's obviously always important to keep the contractor's preferences and materials in mind. And in this case, the pier head false work reused parts and pieces from a trestle that was used earlier on the job. Now I'll hand you off to Jeff Miron, who's the project manager for STG, and he'll finish off our presentation today discussing the challenges that go along with constructing around an airport.
All right, Jeff, you should have control.
All right. Y'all see the screen?
Yes, we can, and we can hear you.
All right, thank you. Thanks, Greg. Thanks, Tony. Like Ben spoke about the design of the Guideway, and Tony, the construction engineering behind the efforts through this area. I'm going to speak to the construction side of it. This section of the job contains some of the more involved, labor-intensive gantry erected spans on the job. The selected gantry was designed specifically, most specifically really, for this 400-foot radius turns in and out of the airport area. Without the range of capabilities made by the launching girder, other means of construction would have been more of a force fit and at a minimum impacted our construction schedule and caused greater expenses. Some of the advantages that the LG provided us is that we had a limited right-of-way, typically through our urban and industrial environment throughout the project. Conventional crane footprints were extremely limited. The gantry provided the construction support that was needed to erect the Guideway through the narrow thoroughfare. Typically, we would have just enough space to get our man lifts and low buoys and different things like that beneath the span to be able to feed the segments by the winch to the gantry. When ground delivery wasn't possible, we would erect the spans via rear feeding and a segment transporter, which is located on the top of the Guideway. The key to this is trying to find a sliver of real estate to set up a crane as near as the gantry as we could. There's a picture in the bottom right corner. You see the segment being transferred through the portal of the RSD after it was released from the segment transporter, and then it'll hang on the rods as shown above, and then we go into the more typical span erection activity. But due to the real estate issues that we had, crane setup was typically 10 spans back down station, and it would cost us at least a minimum of 1 day to try to recoup this or get back on track to be able to roll these segments down the Guideway and get the span erected and keep the gantry moving as we typically could. So by any means necessary, we would try to avoid this and try to rent property or do whatever we needed to do to get the cranes, the conventional crane type, to be able to hang the segment onto the transporter as close to the gantry as possible. We dealt with some different logistical problems around the airport. The post office facility here on the top, there was a construction project going on. The Mauka Terminal expansion of the Hawaii airport for Hawaiian Airlines was being built as we were coming through this area, and different HDOT restrictions. But the multiple groups had to be coordinated with as we erected through the airport area to guarantee the safe delivery without interruption to the businesses. In regard to the post office facility, during the beginning phases, we were denied access week after week from a regional management support level at the post office. And as we recognized it, we weren't going anywhere, and we initiated a different approach to try to get more down to the ground with local management and the different controls in that area involved. Our main intent was to display the overall sequence, have everybody understand what exactly we're doing, and while us learning the rules which had to be followed when working in the area. So from the fact of our construction activities couldn't legally restrict the citizens of Hawaii from receiving mail to require security badging for access to the property, there were quite a few rules of engagement that we had to understand. This one road right here is blown up through this little portal we built. this accommodates a cargo tram that runs through a couple spans of the job. Accommodating this was the number one reason we resorted to that straddle-type falsework tower. The mail carriers would bring mail to and from the planes, and delaying any of this motion would have potentially revoked any of our privileges to try to construct in this area, as we're dealing with not only the post office, and we're dealing with the big boy airlines. So through some ground coordination, we're able to work out a procedure with the post office and best manage our equipment occupying their roads and our overhead loads and different safety measures that we needed to protect our employees as well as their employees. And we're able to figure it out and move through the post office unscathed. The Mauka Terminal project, basically what we needed is this little rectangular area that I'm mousing here to erect the CPS locations at 523 and 524, which Ben was talking about earlier. We needed about a football field side piece of property to bring all of our equipment in, materials, trucks, etc., anything that we would need to be able to erect this area. So the contractor here was obviously building work, and our owner really had little influence with the airport as far as getting us any kind of right of way into this side of the property for us to be able to perform our work. We work for Hawaii and really have nothing to do with the airport. The airport's only letting us come through their property, basically. They weren't going to stick their necks out too far and tell their contractors to stop. And we kind of understood that, but, you know, just because they could have delayed their project or impacted their critical path, there would have been potential civil suits, et cetera, of other tensions that could have been created between the on-site project and the airport as the owner. So when it was all said and done, we were able to coordinate this area successfully with the Mauka Terminal and the post office. And basically the coordinating challenges in the area were simply overcome by knocking on our neighbor's door and building a relationship and making sure that everybody understands what needs to happen and work with each other. This next slide here shows the gantry moving over some ramps and different roadways. And the top tile is highlighted. It shows 8 or so different traffic control plans, which were required for us to be coordinated with to erect through these couple spans near the airport. The spans that had one closure to coordinate weren't too bad to work around the designated times. We had to do some shifting, but typically they weren't as bad. Some of the spans required 3 to 4 different traffic control plans, and we couldn't take a single traffic control plan simultaneously, as it would disrupt, for example, the post office arrival ramps, departure ramps, parking structures, different access thoroughfares through the airport. We had inconsistent allowable ranges of time to operate, varied from one traffic control plan to another. For example, one TCP would be from 9 p.m. to 2 a.m. on Monday through Friday. Another one could be 10 p.m. to 4 a.m. Thursday to Sunday. So the permits were ultimately extending our erection duration cycles and in multiple cases through this area. Working through it was pretty daunting in the beginning, but we were able to find a silver lining and push through some coordination with HDOT and the airport. Other coordination in this area is pretty packed. Ben laid out in the plan view those little asphalt roofs down there are the lay stands. Those guys, we had different taxis, rental car facilities. Further up station coordination was required to work around another contractor that was building the new parking garage in that area and other miscellaneous lots. So coordination and communication, just getting through here was one aspect that was a major challenge. on top of the construction alone. But things worked out well for us here. As I mentioned earlier, the gantry that was designed specifically for these curves, the gantry used its maximum horizontal rotation to erect through the 3-span continuous. The 20-span stretcher guideway used roughly 80 or so disc bearings, and all but two spans contained the uplift type bearings. Now, this range of spans required the bearings to be grouted during the span erection sequence in order to resist the uplifting forces exerted on the spans during the movement in the RSD while launching the gantry. By including the bearing grouting into the erection cycle, this added a couple shifts to the process because of forming and curing. You know, we noticed this is a necessary evil as comparatively to our typical 4-day cycle to support the span erection. So we did whatever we could to try to minimize the additional duration and resorted to procuring a high early grout. Conservatively, this area was the most non-typical portion of the guideway which the gantry erected. To support the gantry kinematics through the varying span lengths along the curve here, we performed numerous gantry reconfigurations. The picture shows us handling a removable element as part of the launching sequence. And from an arbitrary construction start point for you to understand the reconfiguration process, if we were to say we would erect span 1 being right here, we would erect it and then remove the element and launch. And erect span 2, we would put that end element back on. In span 3, we remove the element 7, and then there's another element behind it which is also removable. And span 4, we would add element 6 back on, and span 5, we would add element 7 back on. And all of this is required to maintain the balance of the support beam as we made it through this curve area. In addition to the element handling, the mobile support legs and fixed legs were required to be lengthened and shortened to accommodate elevation changes from the typical capitals to the integrated pier caps. The reconfiguration to the gantry required connecting structural, electrical, and hydraulic components each time a change was made. For example, whenever we were to shorten or lengthen the legs of the gantry itself. So we went from a typical 4-day erection cycle to upwards of 6 to 9 days, depending on the involvement in the added steps. The extended durations beyond the typical span erection were necessary to operate this machine through a guideway alignment design like ours. So the non-typical equipment used became pretty typical in this area. A few areas beyond the airport require some reconfigurations, but not as frequent as in such a short range as this area. Beyond the removable support beam elements, we had some other equipment required to get us through the guideway as well. We had a support beam counterweight, which would pin to the rear section of this support beam and was used to equalize the beam during our launching scenarios. Another example of in a certain instance where we used a pier segment as a counterweight would be suspended from the winch of the main girder, which is the top beam that has the rear support on deck portal, in a situation where we were in a shorter span and the main girder had to launch and had a longer cantilever in front of the 5th wheel. As Tony mentioned, the outrigger towers, we had a special traverse provided to us by the manufacturer that's fixed atop the pier segment here. So as you can see, there's an offset. The traverse actually extends from here over to the tower leg instead of typically it loads directly through the webs of the segment to distribute the load and be able to make our horizontal turn around this area. A couple other pieces of equipment required. They had the segment transporter, is a better picture of the one I was mentioning during the rear feeding on deck. And this is our 350-ton AT truck crane, which we use to mobilize around the job to support different rear feeding events. We had smaller cranes. There's a little football field area that I was speaking of around the 2 CPS piers. We had a 65-ton, which would be used in areas where the 350-ton crane was too big, and we used it to change the legs of the gantry and provide other additional support. Multiple man lifts, as you can see. So it was a pretty involved, pretty busy area of the job. It went well for many reasons, and I'd like to do it again one day. So in closing, I'd like to say that the construction through the airport required an enhanced focus, more resources than we typically use, more efforts, and breaking the ice with face-to-face intros and building relationships, padding up the confidence with these guys to do what we say we can do, and delivering on our word with constant communication was a big reason behind the success of the operation. But beyond the efforts of our joint venture and the design build team, the presence of our original equipment manufacturer supervisor who specialized in this type of machine, and the support received from our construction engineer helped greatly to improve our efficiency and overall performance in erecting the Guideway safely. So I'd like to thank everybody for your time. I hope that you've gained some further insight to our project, and we're now available to field any questions from the audience.
All right. Well, thank you. Thank you, Jeff. That was, and all of our presenters, Ben and Tony, appreciate you joining us today to lead this discussion. We will go ahead and do a Q&A here, and I will hop over. And our Q&A moderator is Mr. Tim Berry with RSNH. He's also the chair of the ASBI grouting committee. He was the previous chair of the ASBI construction practices committee. So you can see here on screen, I won't read all the superlatives about Tim, but certainly has a lot of experience in construction of segmental bridges. And so Tim has been cataloging the questions that have come in during the presentation today. And again, if you have another commitment you need to leave at the top of the hour, certainly we understand. But we will try to answer as many questions as we can, and we'll probably run a little bit past the hour. So with that, Tim, it's yours.
Thank you, Greg. Appreciate it. And so we'll get right into some of the questions that we have. And I think Ben, Tony, and Jeff, I think you'll be able to figure out who will be most appropriate to answer each question. So let me just jump into the first one real quick. Wondering with the tight radius that you talked about with some of the configuration of the bridge, was balanced cantilever ever considered as a construction method? And if so, what drove the decision to stick with span by span?
Well, I guess I could take some of that, and then Jeff, you could kind of take it from the contractor's point of view. But we were able to keep all of the span by span just because of the efficiency of kind of the timeline of it all, and not wanting to introduce new details into the project. So, once we went span by span, it was really kind of to our advantage to keep that technique as the primary technique to avoid basically impacts to the precast yard. When you go balance cantilever, you got to modify your bulkhead, and we would need to make sure we had enough room in the top slab for like cantilever tendons, things like that. So I don't think it was ever discussed in a formal way, but I don't think it would have been the right answer to this.
Yeah, no, I agree with what you say there, Ben. All those facts are true, and they all are the fact of the matter. Another couple things would be the schedule that we had to meet here. As far as like the shafts and the substructure and our permits to be able to get into the airport area, we wouldn't have had time to mobilize the balance cantilever system as well and allow the gantry to progress through in the time that we had to.
Maybe to add one more thing there, doing a balance cantilever would have either significantly altered the equipment design or added additional pieces of equipment, which would have added a pretty significant cost to the project.
All right, thank you. This next one is definitely more design related. Question from the audience. You mentioned uplift at the bearings under service loads. Were there any special evaluation or secondary support needed in looking at that during the design and construction?
So our uplift kind of came from two primary location or sources, I should say. There was a global uplift only, and I think one or two spans. And we tried to tackle that by making those continuous spans. The primary culprit for uplift bearings was what I call compatibility uplift. So as you can imagine, you have a substructure that wants to deflect and a superstructure that wants to rotate. And so when they're working against each other, they want to separate and cause uplift through that bearing. That is, it's not a global instability of the span itself. It's a consequence of having the difference in flexibilities and stiffnesses. So that was something that we were constantly on the lookout for. As far as impacts to the design or the secondary ways of handling it, the uplift bearings are the primary way to handle it. We do have a tie down, but that is basically just sized for ultimate capacity in a seismic event. It's not there for service level uplift.
Okay, thank you. Question: you highlighted the very small section and where you had the reduced box. I wonder what kind of special equipment, or how did you work inside the box? In particular, how did you manipulate the stressing jack to be able to stress the tendon through that area? Which, I mean, he showed that one picture of the what you call the doghouse, and it really looked like an unbelievably difficult space to work in. What techniques did you use to manipulate the jack and maneuver it around and be able to stress those tendons?
Well, typically we would stress from the upstation end, which would allow us some of that access. A couple spots where we had to get on the inside, we would use like drop-in anchors or suspend them from the ceiling of the guideway inside the span. And as far as like access and personnel, there really wasn't a really good way to go about being in there. We thought about creepers and different methods to try to slide along in there, but ultimately until you get in there and try to realize that you can't do that little crouch walk, it's really too short to do that, or like crab walk or anything like that. It was almost like the perfect height to where you just had to bite it and get on your knees and tread through. So we had a couple instances where it was really tight, and handling the heavier equipment, jacks and even plates and strand anchors and different things, where it went from a single person operation, where we would typically use just because of leverage, to where two guys had to communicate and help each other try to fit these pieces into the smaller spot. It was very challenging, and the guys are glad that we're out of there. So.
I bet they are.
And I'll add, if I can, that I think this was one of the benefits of a design build environment where, because we're not approaching an owner with this wonky idea, it's, we're all in it together. And STG, through our constructability review process, was able to make comment, make modifications through the design process that gave them, as minimal as it was, the access that they needed in order to do it through, either temporary top access, putting in those dog houses and the continuous pier segments, or making sure that the deviator blocks are of a right size, and that you're not filling up the entire inside of it with tendons to the point that you can't even get somebody in there with the space that you do have.
Oh, that's great. Yeah, utilizing design build for what it's supposed to be. That's awesome. I wonder if you could go over just real briefly some of the corrosion protection measures that were used on the project to protect the tendons.
Sure. So it wasn't quite qualifying to a protection level 2, which would be specified in the PTI ASBI M50.3, but it leaned heavily on a lot of the FDOT specifications, which Florida DOT is pretty progressive in their corrosion protection requirements. So the overall system was a 4-level system. Cementitious grout, it was black strand, cementitious grout, plastic duct anywhere that we could use it. We did have to use galvanized steel pipe in a few tight radius key locations. From there, you have your grout caps, permanent grout caps, pour backs, and then also an elastomeric coating, or some combination of a pour back and elastomeric coating, depending on the exposure category. So not prescriptive to a PL2, but also pretty darn close. And I'm very happy with the system that we've put in.
Okay.
So that's post-tension corrosion. Sorry, Tim, was it post-tension corrosion protection or just global corrosion protection? Okay.
No, mostly related to post-tension.
Okay.
No, thank you. That was great. Wonder if you could maybe talk a little bit about the casting yard, where it was. Was it a local fabrication yard, or what were some of the details about the casting?
Yeah, the casting yard was roughly 20-25 miles west of this area. We utilized the same precast yard that was used in phase 1 and phase 2 as we acquired it from HART. We had 6 typical segment molds. 2 of those molds were able to accommodate the crossover, wider wingspan segments. And we had 2 expansion joint type molds too, and one of these, which was used to reconfigure into the continuous pier segment molds as well. We had at least, I think we ran with about 2 rebar jigs per mold to try to get ahead of the rebar schedule, and we used an overhead crane over the precast mold and rebar jigs to be able to pour concrete and handle the cages into the molds to continue the short line process. On the way out from the casting, the match cast segment would ride on rails towards a rack that was designed by McNary and those guys to support the segment on temporarily while we performed any repairs and different things like that. So I think the yard itself was roughly neighborhood 35 acres, and it could accommodate close to 1,000 segments double stacked.
Wow. Okay. What was your typical erection cycle for a span? What could you do? How quickly could you, at peak, of course, after learning curve, what was the best you achieved for one span?
I think like 3.5 days. So typically I would say 4 days for a conversation. It's basically hang, glue it, stress it, launch it, each being a day. We got the gantry launcher down to close to about 4 or 5 hours at best.
Wow. And what were your restrictions? Did you have like nighttime restrictions, working around the terminal, working around, you know, what were specific to the airport for work restriction?
Well, the airport, as we approach the departure ramps and that little segment that I ran through, those were more of our restricted times. We were able to work typically Monday through Saturday, even Sunday, just with coordination with HDOT and the Malka terminal job and the post office. As long as we were keeping those guys in a loop, we were pretty good. We had some constraints with the road closures and different things for span erection, but overall in that area, we were mildly constrained, except for over the ramps. Typically around the rest of the job, depending on the capacity of the roadways and traffic hours, we've had to adjust our schedule from a Monday to Friday to Sunday to Thursday as we got closer to the highways and busier areas.
Okay, finally, one last question. I wonder if somebody could give a rough estimate of what the cost of the gantries were. It's a question we get quite often, especially relative to the cost of the project. Just give us a sort of a rough estimate of what the gantry cost was.
The gantry cost itself, we purchased 3 gantries, 2 of these articulated types and 1 conventional type, and we're somewhere in the range of $12 million.
Okay. All right. Well, Ben, Jeff, and Tony, thank you very much. It was a really, really cool presentation. What a cool project as well. And thank you for taking the time to answer these questions. And Greg, I'm going to turn it back over to you.
All right. Well, thank you, everybody. I appreciate those of you who hung with us. Looks like the majority of the audience was able to hang with us here through the Q&A. We ran about 10 minutes past the hour. Again, appreciate everybody who attended today. Thank you to our presenters, Ben, Tony, Jeff. Can't thank you guys enough. Love this project. I wish ASBI would fund me to go visit it. So fantastic project in a great location. Again, to all our attendees, if you're not following us on LinkedIn, us being the American Segmental Bridge Institute, I'd encourage you to do so. And if you have any questions or comments about this session, you see the email address on screen. You could just pop an email there. And again, if you give it about a week to get your certificate from attendance today, we'll send out those from RCEP. If it's more than a week, you can shoot us an email again at this address to say, hey, I haven't seen my certificate, but we generally haven't had those follow-ups. I know one person mentioned that today in the question, and we'll take care of that one, but otherwise you should get your certificates. So again, thank you, everybody. And with that, we will conclude the webinar.
Thank you.